This is part 2 of our video series on the fundamentals of solar panels. In this video, we're exploring how photovoltaic cells actually work. We'll break it down step by step, starting with the basics of semiconduction, the p-n junction, and the photovoltaic effect in a photovoltaic cell. By the end of this video, you'll have a clear picture of the science behind how solar panels turn sunlight into usable electricity. All this is possible because of a material called a semiconductor. Even though semiconductor materials come from different groups of the periodic table, they share certain similar properties. Most common semiconductor materials include aluminum, silicon, phosphorus, sulfur, copper, zinc, gallium, germanium, arsenic, selenium, cadmium, indium, antimony, and tellurium. Or a semiconductor can be a compound made of two elements such as gallium arsenide, indium phosphide, or cadmium telluride. It can also be an alloy, for example, alloy made of silicon and germanium, or aluminum and gallium. The size of the band gap is what differentiates conductors, semiconductors, and insulators. The band gap is the minimum amount of energy required to excite an electron from the valence band to the conduction band. When a semiconductor gets energy at least equal to the band gap, the electron is excited to a free state, which can now participate in conduction. A hole is also formed at the spot where the electron was previously present. This hole also plays a role in conduction. Doping is done to increase the number of free electrons or holes in a semiconductor, therefore enhancing its electrical conductivity. N-type doping increases the number of available electrons, and p-type doping increases the number of available holes. An interesting phenomenon occurs when joining n-type material with p-type material. This joining causes excess electrons in the n-type material to diffuse to the p-type side, and excess holes from p-type diffuse to n-type side, creating an electric field in between, which is called depletion layer. This electric field results in a voltage developed at the junction. The p-n junction diodes are the basis for all electronic devices, not only solar cells, but also other electronic devices like LEDs, lasers, transistors, and many more. When voltage is applied across the p-n junction such that electric field at the junction increases, such arrangement is called as reverse biased. At this arrangement, the electric field at the junction increases, thus decreases the probability of carriers to diffuse from one side to other side. Whereas, in forward bias arrangement, the electric field is applied in such a way that the electric field at the junction is reduced. In such condition, the depletion layer is decreased, and the carriers can more easily pass through depletion region. In this condition, current flows through the circuit. Now, let's talk about the solar cell. A solar cell, by definition, is an electronic device that converts sunlight into electricity. A solar cell uses a photosensitive semiconductor material. In practice, almost all solar cells use semiconductor material in the form of a p-n junction. When a photon from sunlight is absorbed by the material, it generates electron-hole pairs. If we simply leave the p-n junction without any external connection, those electron-hole pairs will recombine and nothing useful happens. But if we connect a collector and an external circuit, then the generated electrons are pulled through the external circuit, forming a current flow. This is how a solar cell generates electricity.
Interesting facts. Different semiconductor materials have different band gap energies, and they are typically measured in electron volts. Condition number 1. What happens when the energy of the photon is less than the band gap energy of the semiconductor material? Answer is nothing happens. The photon's energy is absorbed and dissipated as heat or other non-useful forms of energy. Condition number 2. What happens when the energy of the photon is equal to the band gap energy? In this condition, the photon is absorbed and it excites an electron. In this case, total useful energy transferred is equal to the band gap energy. This is the most efficient condition for energy conversion. Condition number 3. What happens when energy of photon is greater than band gap energy. In this condition also, photon is absorbed and electron is excited, but total useful energy remains same and equal to band gap energy. Remaining energy from photon is converted into heat.
Now these facts leads to a question. If a single cell can produce energy only equivalent to band gap for a single photon, then efficiency of solar panel for a particular cell is constant. So how can we increase the efficiency of solar panel? The answer to this question is to stack the solar cells of different materials on top of each other in such a way that cells with highest band gap are placed at the top and the cells with lowest band gap are placed at the bottom of the stack. By this method, 1. Light with lower wavelengths are absorbed by the top cells and remaining light with higher wavelength are passed to the lower cells. This will allow a wide range of spectrum to be absorbed. 2. Since wide range of spectrum of light is absorbed, the losses due to heating is also reduced. So, the final question is, why don't we use multi-junction solar panels on our houses to get high output? This would be really nice, but these multi-junction cells are 100x more expensive than regular solar cells. That is why they are only used in research and space missions.